So now let's look at how to do this with pointers. So for example, previously we had this variable address underscore of underscore a pointing to a. Now let's modify it and make it to point to a2. To do that, we can first query what is the address of a2 using the ampersand operator, and then save the memory address in this variable address underscore of underscore a. So once I execute this line, we should see address underscore of underscore a2 using this variable address underscore of underscore a, which is this new address, which is different to what we were referring to before. So let's look at the new address. So let's copy paste it into the memory window, and now notice it's pointing to a2 and its value is equal to 30. So this again showed that we can use one single pointer variable and make the pointer variable point to different memory addresses based on where what is the current memory address that's stored in this particular variable. The pointer points to that variable. However, this cannot be done with references. Once we initialize a reference to point a certain variable, it always refers to the same variable. We can use the reference to modify the content of the variable. We will see more examples of where we use references when we go back to functions. For now, just think about pointers and references are means of accessing the address of a variable and means of modifying the value of that variable. Okay, so now we can use the variable address underscore of underscore a and dereference it with the dereference operator to access the value of a2. So let's print a2 using address underscore of underscore a. Notice a2 is equal to 30. So pointers are convenient ways of accessing variables through memory addresses. Now, it's not required that you initialize a pointer when you declare it. So for example, in line 72, I'm declaring a variable called address. Its type is int star, so it's a pointer to an integer variable. However, we're not initializing it with an address. So what happens? So let's first stop this program. Let's put a breakpoint here, uncomment this line, and let's see what will be the value stored in this particular variable address. So is the variable address initialized or not? Now notice this already gives us a compilation error. The compiler here says that uninitialized local variable address used. That is, with pointers, if we don't initialize a pointer, we are not allowed to print its value. That is, we are not allowed to access this pointer without initializing it. So this provides a compilation error. So therefore, we need to first initialize it. And to initialize it in C++, we use a special value called null pointer. So null ptr is the special value in C++. It is not the same as null or zero in C, so it's very important to know that. And also, it is important to not use null or zero instead of null ptr in C++. I won't go to the details of why you should not be using null or zero, but remember, null ptr is the default initialization for pointers in C++, and we should not be using null or zero instead of it. So now in line 79, I am initializing address with null ptr, which means that this particular pointer is not pointing to anything, or it's pointing to void or nothing. Next, I'm modifying the variable address to point to address underscore of underscore a. We saw that address underscore of underscore a was pointing to a2, so now address will also point to a2. So we have two let's see. So we have two pointers in our program now. First pointer was address underscore of underscore a. The second pointer is address. However, both of them are pointing to the same memory location. That is, both of them are pointing to the memory location that holds the variable a2. Now, a good practice in C++ is to first check whether the address is null pointer or not. That is, whether it is pointing to something valid or not, and only dereference it when it is not a null pointer. So here in this if condition, I'm checking whether address is not equal to null ptr. If it is true, Then we dereference address and print its value, print the value stored at that particular memory location. So let's continue and check what is the value stored in the memory that is pointed to by address, and notice the value is equal to 30. So again, what this means is that address is pointing to variable a2, which was equal to 30. Now let's look at some pointer arithmetic. That is, previously I already showed you that you can use the dereferencing operator along with the variable name to do arithmetic. Now let's look at some more examples. So here I'm declaring a variable called b, its type is double, initialized to value equal to 3.14. Then I'm taking the memory address of this variable b in this pointer address underscore off underscore b. So remember, when ampersand is used before the variable name on the right hand side of an assignment statement, we are referring to the memory address that holds this variable b, and we are storing that memory address in the variable address underscore off underscore b, which is of type double star. Now it's illegal to store the address of a variable that is of type double in a pointer that is of type integer. So we know address underscore off underscore a points to an integer, while address underscore off underscore p points to a double. So now if we try to make this assignment, this should give us a compilation error. So let's stop the program and compile. Now notice we got an error in line 107, which is this line, and the error says that equal to cannot convert from double star to int star. So there is no implicit conversion from one pointer type to another pointer type. So this provides us an error. However, when we have two pointers of the same type, here in line 111, I'm declaring another double C of with initialized with value equal to 5.0, and address underscore off underscore C is now pointing to this variable C. Now we can check whether these two addresses are equal using the equal to operator. So here in line 118, I'm checking whether address underscore off underscore C is equal to address underscore off underscore B. If it's equal to, then we will get a true. Since I'm using std : bool alpha, we will see either a true or false on the console. If they're not the same addresses, we should see a false. Now, we know that b and c are different variables, so they must be having different memory addresses. Therefore, when we check this address underscore off underscore C is equal to address underscore off underscore B, we should get a false, which is what we saw on the console. Okay, so now let's see how to take the difference between two addresses. So the difference between two addresses is also a memory address, and we can store the difference in a type called std : ptr diff underscore t. So this is a special type within C++ that is used to store the difference between two memory addresses. So we can store now the difference between address of B and address of C, and then print its value using this cout statement. So let's check what's the difference between these two addresses. Now notice the difference between these two addresses is -8. So first, this std : ptr diff underscore t is of type signed, so it can both store both positive and negative numbers. And second, it holds the difference of two addresses. Now since we are working on a 64-bit computer, the difference between two integer memory addresses is equal to 8 or 64 bits. So it's 8 bytes or 64 bits.